There is a real possibility that millions of signals from extraterrestrial intelligence are reaching our antennas right now. However, what if we are not listening properly and missing them? Narrowband signals are the preferred method to search for extraterrestrial intelligence, but what if those signals are being distorted before they even reach us? What if the very stars these civilizations orbit are masking their existence? The Exoplanetary Interplanetary Medium, or Exo-IPM, is a region surrounding planets in an extrasolar star system, shaped primarily by the activity of the system's host star. Commonly referred to as the space weather region in a planetary system, this region is mostly made of ionized gas, stellar wind, magnetic fields, coronal mass ejections, and stellar flares. This space weather can distort potential narrowband signals coming from an alien civilization and potentially make them undetectable by our current SETI detection methods. Is there a solution for this? Hello, I'm Dr. Alejo, and welcome to another episode of the WOW Contact. Thanks for joining me in this video. We have recently reached more than 700 subscribers, an incredible milestone. If you are one of those subscribers, thank you so much for your support. If this is the first time you watch any of our videos or haven't subscribed just yet, I invite you to become part of this growing community. Let's jump into today's video. I recently had the opportunity to attend the 404 International Astronomical Union Symposium, which was held entirely virtual during the first week of March 2026. The symposium focused on seeking the advanced in the search for technosignatures, gathering professionals in the SETI field who presented their contribution and ideas on the theoretical, instrumental, observational, and data analysis fronts. The main topic was to discuss ways to advance the search for technosignatures by taking advantage of data collected by existing missions and from data already present in data archives. Out of all the many talks and ideas, the one that caught my attention the most was the idea that perhaps we already have in our hands data containing signals generated by an alien civilization. Such signals could be hidden or altered in a way that we haven't accounted for. Join me to explore how the very same stars that a civilization planet is orbiting could be making the detection of alien signals a hard challenge for SETI researchers. On Earth, we humans communicate using a variety of radio waves. When I was a kid, many years ago, smartphones and the internet were not a thing. I know many of you cannot conceive such a thing, but it is true. Radio receivers were widely used to listen to your favorite radio stations. These were stations that usually had names relevant to the frequency you had to set your radio receiver so you could pick up their signal. 96.5 MHz, 92.1 MHz, etc. All these radio stations still keep those frequencies in their names, even though you don't need a radio receiver anymore, as pretty much all the radio stations have a presence on the internet nowadays. Radio stations used what are known as narrowband signals. Narrowband signals transmit information on a fixed frequency, so it is easy for someone to receive and decode the transmitted signal. But narrowband signals are also optimum for the transmitter of the signal. These signals are ideal due to their minimal energy requirements. That is, it takes less power to transmit them and are less likely to be confused with emissions caused by natural phenomena. Natural astrophysical emissions, for instance, are in their majority broadband signals. Broadband signals are noise-like and spread across a wide range of frequencies. In particular, SETI researchers tend to focus their search efforts around what it is called the waterhole frequency. This is not a specific frequency, but a range that goes from 1420 MHz to 1720 MHz. It is expected that a technologically advanced civilization may use this range for transmissions due to its significance in the universe. Hydrogen atoms emit at 1420 MHz, which corresponds to a wavelength of 21 centimeters. Hydroxyl molecules, which are composed of one atom of hydrogen and one atom of oxygen, emit at 4 specific radio frequencies, ranging from 1612 MHz to 1720 MHz. When a hydrogen atom combines with a hydroxyl molecule, this results in a molecule of water, which is the most essential molecule for life as we know it. In a previous episode, we talked about the WOW signal, which is the most promising technosignature candidate ever registered. I will leave the link for you to check it out. But what if one of those narrowband signals gets distorted, and by the time they reach our instruments, they look like broadband signals? In a paper titled Exo-IPM, Scattering as a Hidden Gatekeeper of Narrowband Technosignatures, the authors explore how the space weather of a star can distort and disperse possible extraterrestrial signals. There are two main ways how a signal can be affected. The first one is temporal scintillation. This is a flickering or twinkling effect in time, similar to how stars appear to twinkle in the night sky. As signals traverse regions in the interplanetary medium, or IPM, they encounter irregularities in electron density, turbulence in plasma, and moving structures in stellar wind. This causes the signals to sometimes focus or appear brighter, or to defocus or appear dimmer. The second effect is referred to as spectral broadening. This occurs when a signal that had a very precise frequency, a narrowband signal, spreads out over a range of frequencies. Motion of plasma, turbulence, and scattering cause the signal's energy to spread out, reducing its peak strength and making it harder to detect. This effect was first observed for the probes Mariner 4 and Pioneer 6, and then with the Helios 1 and 2, Pioneers 10 and 11, and Viking. For all these probes, spectral broadening was observed to peak near the Sun and decrease following a power law as the probes got away from the Sun. Given that our Sun was observed to cause such effects in human technosignatures, it is only expected that signals from other potential civilizations would face the same fate, making it harder for SETI researchers to detect such signals if our pipelines don't correct for such effects. To address this, the authors model how a signal is altered as it travels through the turbulent environment of an exoplanetary system. They treat the space around a star as a moving, chaotic plasma, similar to the solar wind in our own system, filled with fluctuations in electron density. These fluctuations act like a constantly shifting lens, distorting the signal as it travels through space. Using a well-established model of turbulence known as Kolmogorov turbulence, they link the strength of these fluctuations, the speed of the stellar wind, and the distance from the star to predict how much the signal will spread in frequency. The results show that the closer a signal passes to its host star, the stronger the distortion becomes, following a clear power law relationship. They also include extreme space weather events, such as coronal mass ejections. While rare, these events can dramatically increase turbulence, causing signals to spread by orders of magnitude more than under normal conditions. At the same time, this same turbulent environment causes the signal to flicker in time, meaning that both spectral broadening and temporal scintillation are not separate effects, but two sides of the same physical process. By combining all these factors, turbulence, motion, geometry, and stellar activity, the authors built a framework that predicts how a clean narrowband signal can be transformed into something much harder to detect. To make their model realistic, the authors didn't just work with abstract physics. They used real stellar environments. First, they used our own Sun as a baseline, because, as we mentioned before, decades of spacecraft data have been collected, so researchers already know how signals get distorted as they pass through the solar interplanetary medium. Using this data, they calibrated their model, deriving how spectral broadening changes with distances from the star and validating the underlying physics. But not all the stars in the universe are like our Sun. As a matter of fact, the most common stars in the universe are M dwarfs. So the authors extend their model to this type of stars. M dwarfs are also of high interest for SETI researchers as possible stars hosting planets with extraterrestrial civilizations. One example of an M dwarf planetary system is the famous TRAPPIST-1 system, a system with 7 rocky planets. M dwarfs are extremely long-lived, which could make them ideal hosts for ancient and potentially very advanced civilizations. Since astronomers don't have direct measurements for those M-dwarf systems, the researchers scaled the solar model by adjusting key properties like stellar wind, strength, turbulence levels, and activity. They then calculated how much each signal would be broadened as it travels through the Exoplanetary Interplanetary Medium. Once the model was completed, the authors simulated an entire survey of about 1 million nearby stars. In this simulation, they modeled how a narrowband signal from each system would be affected by its local space environment, taking into account factors like the type of star, the geometry of the system, and the conditions in the surrounding plasma. Around 1 GHz, the frequency range where many SETI searches operate, about 70% of systems produce more than 1 Hz of broadening, and over 30% exceeds 10 Hz. At lower frequencies, the effect becomes even more extreme, with many systems showing broadening of hundreds of hertz. What this means is that across a large population of stars, a significant fraction of potential signals will no longer appear as the narrowband signals our detection pipelines are designed to find. Signals coming from planets around M-dwarfs are expected to experience much stronger distortion because these stars tend to be more active and turbulent than the Sun. This means that a large fraction of potential technosignatures, especially around the most common stars in the galaxy, could be significantly distorted and weakened before they ever reach us. In other words, even if alien civilizations are transmitting, our searches could be ignoring them simply because they don't look the way we expect them to look. We could be missing millions of signals coming from extraterrestrial intelligence, not because they don't exist, but because we are not listening the right way. What if aliens are transmitting right now their own versions of Encyclopedia Galactica, a famous fictional compendium of all human knowledge in a galaxy-spanning civilization? If alien signals are being distorted before they reach us, then the solution is not necessarily to build bigger telescopes, but to look at the data differently. The authors suggest that our current SETI pipelines designed to detect extremely narrow spike-like signals may be too restrictive. Instead, we need to adapt our search strategies to account for distortion. Rather than looking only for ultra-narrow signals, we should also search for signals that are spread over several hertz or even hundreds of hertz. In other words, we need to look for signals that are blurred, not perfect. This is where AI and advanced signal processing come in. Instead of simple filters, we can use pattern recognition, machine learning, and anomaly detection. If we understand how Exo-IPM distorts signals, we can try to reverse the effect, like correcting for atmospheric distortion in telescopes. One of the implications of us missing these signals is that this could explain the great silence we observe. Concepts such as the gray filter have been proposed to justify why we don't hear from other civilizations. We have a full video dedicated to this topic. However, it could be that our instruments are not tuned properly to detect those signals, which could explain why we haven't heard anything. One more time, thank you for watching and being part of this community. That's it for now, and remember, the truth is out there.